Welcome to the Laboratory for Electrochemistry at PSI. I am Denise Verhoeven, the laboratory head. The Laboratory for Electrochemistry here at PSI focus on energy storage and conversion. We develop technologies, processes, and everything needed that allows us to have environmentally friendly energy provision and consumption in the future. We do this with our 5 groups currently, 3 of which are focusing on hydrogen-related topics and 2 are focusing on battery-related topics. Currently, we are about 60 people in the lab. That spans all the way from bachelor students to very experienced scientists and group leads. And it's my pleasure to introduce the lab to you right now.
My name is Lawrence Gubler and I'm a materials scientist and I'm leading the group called Membranes and Electrochemical Cells here at PSI in the Electrochemistry Laboratory. My main responsibility is the scientific content of the group and the working topics of the team members. This is the membrane lab where we prepare membranes for later testing and we're going to see what Torben is up to at the moment. Hey Torben.
Hey.
How's it going?
Pretty good. I'm just testing our new membranes. Hi, I'm Torben Saatkamp. I'm a chemist working in the Membranes and Electrochemical Cells group as a scientist, where I support Lawrence and the group in our effort to develop new generation membranes for electrolysis and fuel cell applications.
Okay, sounds good. Our main focus is to push the boundaries of understanding of these materials, ion-conducting membranes, in electrochemical conversion devices such as fuel cells and electrolyzers. In particular, we try to understand the limitations of durability and lifetime in the cells.
Yeah, the membranes in fuel cells and electrolyzers are essential because they have a very complex property profile they have to provide. They separate gases, they conduct ions, and they make sure that the device runs efficiently and for a long time.
We have these types of cells which operate at low temperature. They have a polymer membrane that separates the 2 electrodes, which we have on either side. And therefore they need to separate the half-cell reactions, so for hydrogen evolution and oxygen evolution for a water electrolyzer, for example. But at the same time, the membrane is the polymer electrolyte, so it needs to conduct ions from one side to the other. And ensuring both at the same time, having a thin membrane while it is still working as a separator for ideally thousands or 10,000s of hours is a challenge and one of the things that we are addressing.
So this year we were able to show that our next generation membranes are particularly useful in water electrolysis application, where we could show that very thin membranes that are very conductive but also durable make a big difference in the overall lifetime of a water electrolysis cell. The most important effect that you can see is the reduction of resistance of the membrane. This straightforwardly feeds into higher efficiencies, but at the same time new materials reduce cost and overall investment costs that these new technologies require. So one of the key contributions that we do in our group is that we focus not only on the performance and the conduction, the transport properties of these membranes, but also we look at the total lifetime, so the durability, degradation behavior, and this is something that will be seen once you deploy those technologies, you bring them into application, because we try to make sure that they run for decades and ensure that we can have hydrogen as a cheap resource. Hydrogen is a very versatile energy vector, so it allows the storage and the transport of energy as a chemical bond in time and in space. So versus batteries, we're often trying to showcase how hydrogen makes storage and transport much easier. It can be used in steel production as a chemical, as a resource, but also can be used to re-electrify applications such as transportation. For example, heavy fuel cell trucks are one of those applications.
So the type of membranes that we're working on are essential for these electrochemical cells. However, they also contain electrodes with electrocatalysts. And for that, I would like to introduce to you the Electrocatalysis and Interfaces group.
Hi, Ken.
Hi, Emmy. How are you?
Good, you?
Oh, you know, the usual. Capacitance never correlating with anything.
I'm Kenneth Crossley, and I am a PhD student in the Electrocatalysis and Interfaces group at PSI. Our group is generating knowledge, which helps us to develop better materials that are more cost-effective and more earth-abundant, more environmentally friendly for producing and storing and converting renewable energy. Catalysts are important for hydrogen production and synthetic fuels, especially in the future when we're going to be trying to power lots of our economy on renewable energy sources. We have been using oil as an energy storage and transportation vector, and we're moving towards using hydrogen as this because it's a carbon neutral molecule. We have water as an emission product when we burn it or couple it together in a fuel cell in a reaction. Catalysts work a little bit like Google Maps in that we have a starting product and an ending target product, and they help the reaction to find the fastest or a more efficient way of getting from A to B than we normally would just by applying heat. These catalysts help us to create the molecule, split water into hydrogen and oxygen, where we can then keep the hydrogen for the energy storage. And we can do this in a more efficient manner. So we can use less power, less energy, and create more product. One of the main focuses of the group is we are trying to understand how these catalysts behave and change during the reaction so we can design better ones. We are trying to move away from precious metal-based catalysts, which are very expensive and very rare in their distribution on the Earth, towards more environmentally friendly and earth-abundant materials like iron, nickel, and cobalt. This year, we've been able to use what we learned at the synchrotron and what we have in the lab to understand why cobalt oxyhydroxide and cobalt-based oxide materials in general have a pH-dependent activity. We have been able to show that the flat band potential controls the onset of the oxygen evolution in cobalt-based catalysts across the pH spectrum, from pH 13 to pH 1 or 0. And this will help us to understand how to improve cobalt-based catalysts in the future. But making materials isn't really enough. In order to understand how these materials interact with one another and are integrated and built up into a working device, we rely on our colleagues in the fuel cell and diagnostics group.
My name is Juan Herranz, and I'm the leader of the Fuel Cell Systems and Diagnostics group here in the Electrochemistry lab of PSI.
My name is Zarina Turtaeva. I'm a postdoctoral researcher at the Fuel Cell Systems and Diagnostics group here at Laboratory of Electrochemistry.
So the main focus of the group is to work with what we call porous media, so materials that have high porosities to be able to transport matter, so liquids and gases, in fuel cells, in water electrolyzers, and also in CO2 electrolyzers. What we do is that we improve basically the performance of these devices. These porous media are very relevant specifically when the devices need to operate at, for instance, high current densities. So the better the materials that we produce, the better is going to be this performance, and therefore basically the more efficient that the technologies are going to be. And then specifically in the context of this porous transport layer, it's about efficiency, but it's also about cost, because with these new materials, we are able to use less catalyst, and that actually has a big impact on the cost of the whole device.
Okay, so now so that you can see how we work with the other groups within the laboratory, we are going to show you how we take the membranes from the membrane group and the electrocatalysts from the electrocatalysis group, and we put them together in what we call a spraying machine, in which we put the catalyst on the membrane. And for that, actually, we are going to go to my colleague Sarina, because she's actually the one who is going to operate and operates very often this specific machine, this spraying machine. So Sarina, could you please explain us a bit what you are doing and how this machine works?
Sure. Here we have a catalyst ink made with a catalyst provided by a catalyst group, and we have also stable membrane provided by membrane group. What we do, we place this membrane here inside of the spray coating bench, and the catalyst ink would be inserted inside of the syringe, and would be going through all the way to the nozzle and spray to the active area of the membrane. So at the end, we will receive what's called catalyst coated membrane, CCM, which will be later assembled inside of the cell and tested inside of the test bench. We also use advanced X-ray field techniques to visualize structures of the PTL, like porous transport layer, also do operando measurements to study water distribution inside of the pore structure, as well as visualize how evolves this material inside of the test bench, and study the performances of these electrolyters.
So one of the main discoveries or breakthroughs has been in the context of what we call porous transport layers. So these are, again, porous materials that we put into electrolyzers, water electrolyzers specifically. And actually, they are heterogeneous materials with different kinds of porosities that we can tune. And in doing so, what we managed to do is that we managed to get a better utilization of the catalyst that we also need to have in the electrolyzer. And this is actually something that is very important, because by utilizing the catalyst in a more efficient way, we also manage then to be able to use less catalyst in these devices. And in water electrolysis, the catalyst typically is based on iridium, which is actually a very expensive and rare metal. So in the end, what we are doing is helping to decrease the cost of this technology. So we managed to get the same performance that we used to have, but now we need to use 5 times less of this catalyst, this iridium, which is, as I said, very rare and also very costly.
It helps make energy sustainable and improve the performances of the fuel cell or electrolyzer.
So our research here makes sure that devices like electrolyzers operate in a more efficient way, but sustainable energy is only one part of the equation.
You know, over the last years, we have grown year by year by year, but we are still missing some important topics and skills. So we are adding an additional group to what we already have. However, with this, the organization becomes too big to manage easily and to be agile enough to really make an impact on science. Therefore, we have decided to split the lab into 2 labs. One will stay the electrochemistry lab, focusing on hydrogen-related research, and the other part will be the laboratory for battery science in the future. That lab will be led by Sarbajit Banerjee, and I would like to introduce him to you right now. So please join me in welcoming Sarbajit to PSI. It's a pleasure to have you here.
Thank you, Dennis.
The Laboratory for Battery Science is a natural evolution of energy storage research at PSI. PSI has a long history of seminal discoveries in energy storage, and we're taking this great legacy of energy storage and conversion research in a new direction, really emphasizing energy storage solutions that will benefit all of humanity and that will scale from fundamental science to actual practical technological solutions. In the next few moments, you're going to see some of the great research being done at LBS to make our ambitious vision a reality.
My name is Samuel Gatti. I'm a third-year PhD student, and I'm on a shared position between the LEP lab and the Battery Electrodes and Cells group at PSI.
My name is Leon Skarian. I'm a PhD student in the Battery Electrodes and Cells group in my 2nd year now.
The Battery Electrodes and Cells group is mainly focusing on new materials for high energy density batteries to make them more safe, more cost effective and environmentally friendly. The work of our group mainly focuses on liquid-based electrolyte systems, whereas the other battery group mainly focuses on solid-state electrolytes.
We are pairing established electrochemical methods with the use of operando methods that we have in-house, such as our X-ray diffraction device, as well as the online electrochemical mass spectrometry. And we are also using the facilities at the other side of PSI, mainly for X-ray techniques such as absorption spectroscopy and neutron imaging.
So now we have our freshly assembled cell, so now we want to test it. And for that, we use battery cyclers and a temperature chamber. So we connect our cell on one of these channels, and then we move on to start the program. Great. So we have our cycling program ready and are about to review it for one last time and start our cyclic voltammetry experiment.
One way to increase the energy density of lithium-ion batteries is to replace the graphite anode with metallic lithium, meaning that you're not storing the lithium in a lattice material, but reducing it to metallic lithium. And this brings different challenges because the dynamics of the system is completely changed. And one of them is the formation of dendrites, which we call tree-like metallic lithium structures. It is believed that lithium dendrites form when lithium is deposited inhomogeneously, meaning that the reduction occurs on isolated spots, forming island-like structures, which then throughout prolonged cycling can cause fatal short circuit. We can use electron microscopy to get a first picture of the plating morphology, the deposition morphology, once we open the cell. One of our big achievements is the kickstart of a collaboration with the Applied Materials group from the Laboratory for Neutron Scattering and Imaging. With this group, we are closely collaborating to develop new methods of neutron imaging with a particular focus on lithium batteries. Now, we're also able to observe the lithium deposition operando during charge and discharge, which is of particular use to us because we do not have to modify the system that we're interested in, which is unavoidable if you're using ex situ methods. In other words, when you have to open up the cell and firstly wash it, for instance.
We also work together with the Battery Materials and Diagnostics group on a lot of advanced characterization, for example, on surface characterization and so on. So our collaborations with the BMD group mainly focus on our complementary analytical competencies, and this allows us to have several joint projects, but also joint publications. So let's hear what the Battery Materials and Diagnostics group did during this year to contribute to that.
I'm Valerie Siller. I'm a postdoc in the Battery Materials and Diagnostics group.
My name is Lingfeng Xu. I'm a PhD student at the BMD group. I'm mainly working on characterization of solid-state battery based on X-ray computed tomography.
So the BMD is working on all solid-state lithium-ion and lithium-metal batteries for enhanced energy density and safety. The goal of the group is to understand what happens at the interfaces of such all-solid-state batteries, ideally during battery operation, as this avoids to manipulate the cell in addition or even destruct it. All solid-state batteries feature many complex interfaces because they combine a cathode active material with a solid electrolyte and a composite. This composite cathode is separated by the solid electrolyte from the anode, which is ideally lithium metal, as it enables us to use highest energy densities. After, when we place our cathode composite on one side of the separator, on the other side, then we place our anode, which in this case is the lithium metal anode, and then we apply a constant pressure through the frame of the cell throughout the entire battery operation to ensure a good interfacial contact in all of these many different interfaces that we have in our solid-state battery. This is Robin Wullig, one of our PhD students, working mostly on our standard electrochemical cells for the assembly of all solid-state batteries. Those are new cell designs which potentially also allow us to cycle the all solid-state battery outside the glove box, as it has an improved tightness to the previous design. Here we assemble everything inside the glove box because we work with air-sensitive materials, or also materials that are very sensitive to humidity, so they're not made to be processed in the ambient atmosphere.
The implementation of lithium metal on solid-state battery has many different challenges. The first major problem is that the growth of lithium dendrite and crack propagation, which might lead to a short circuit of a battery, and that can be fatal for the battery. In hospitals, we often use X-ray CT to examine human bodies, right? Here, in our group, we also use similar XCT technology for an inspection of our solid-state battery. With high brightness synchrotron X-ray source, we can scan our battery with high spatial and time resolution in real time. With advanced 3D image reconstruction method, we can visualize and identify different failure mechanisms inside batteries. So this is a specific cell design for operando XCT measurement or computed tomography measurement for our solid-state battery. The frame of the cell is 3D printed, and the core part of the cell is this tiny little PEEK tube with diameter only 3 mm. which is much smaller and thinner than our standard solid-state battery cell design. We designed it to be smaller in order to get high transmission signal after the X-ray, and this is for the better quality of the tomography data. It is very difficult to manufacture lithium metal at large scale due to different risks on safety and contamination and so on. That's why our group also put our focus of research on zero-axis lithium metal solid-state battery. That means we'll just use lithium ion already present in the cathode. A promising pathway is to add an additional nucleation layer on the current collector. In 2024, we have demonstrated that just 50 nanometer of silver coating has already a major improvement on the cycling performance of solid-state batteries. And secondly, we were able to perform the operando XCT on cycled metallic lithium, which was a quite challenging experiment, not only because of the specific requirement on the operando cell design, but also visualizing the metallic lithium with advanced 3D image reconstruction method.
So despite the widespread use of batteries for energy storage, they still face many challenges concerning their longevity and safety. And this requires distinct characterization techniques that allows us to understand and monitor the real-time battery failure, and this will help us to improve battery performance for the future.
I hope you enjoyed this video, and I hope we were able to provide some insights for you. Each of the newly founded labs, so the future leg focusing on hydrogen-related topics, and the Laboratory for Battery Science, will have each their own vision, mission, and strategy. However, we are strongly interlinked, so we spend a lot of time this year discussing what our similarities are and what our differences are, because each one of us needs to work on its own profile. But we decided to have joint events, we will have joint instrumentation, and certainly also joint projects in the future. It is our future mission, as it has been over the last years, to support the activities all around the world to reach the net zero goal and to make sure that we have a sustainable future. Thank you.